Okay, welcome to the probability section of our class. Sometimes this is a little bit more difficult for a lot of people than the rest of it, mostly because it's just kind of some of the concepts are a little bit weird. We're thinking of everyday normal things in a little bit different way. So I have my joke, of course, in the front. So let's start talking about probability for equally likely outcomes. Equally likely outcomes, things like rolling a dice, choosing a marble out of a bag. So let's say that we're choosing a marble out of a bag, and the probability of choosing one certain marble is equally likely of choosing any marble out of the bag. So if we say we have 3 blue marbles, 2 red, and 5 green, 2 blue, 5, what did I say? 5 red and 3 green, something like that. Then what are the chances of drawing a blue marble? Well, since each marble has an equal chance, that means that I have 2, because that's the number of ways that I can get a blue marble is 2, over the total possible number of outcomes. Well, I have 10 marbles. So it's 2 out of 10 or 0.2 or 1/5, however you want to write it. I have a lot of people who ask me how they should write probabilities, whether I want them in decimal form or in fraction form. Generally speaking, if it is a fraction that makes sense to you, like what makes sense to you? 1/2 makes sense. I can picture that in my head. 1/3, 1/4, 1/5, a little bit, 1/6 maybe, 1/8, things like that. I can picture these in my head. I can even picture, we can picture 3/4 or 2/3. What I can't picture is 62 over 118. That's a little bit harder. It's close to 1/2, but it's more difficult to picture exactly what's going on with this fraction. So, or that could be reduced. Let's say 61 over 118. But this I don't know. This I would want to be in a fraction form or in a decimal form so that I can see it a little bit better. Here, any of these can be in fraction form. So if you think you can picture it, then I can probably picture it. It's not something I'm a big stickler for, but things like this, I don't know what 61 divided by 118 is. Like I said, it's somewhere near 0.5. It's a little bit more, I think. But I can't picture that in my head, so I want to see that in decimal form. So let's talk about examples of probability. So the probability of rolling a 3 on a fair die. Well, how many ways is there to do that? There is one way. There are 6 different numbers on the die, so it's 1 out of 6. Probability of rolling an even number. Okay, on the die, there's 2, 4, 6, so there's 3 ways out of 6, which reduces to 1/2. Probability of rolling a number more than 4. So that's strictly more. I didn't say greater than or equal to, or I didn't say at least 4. I said more than 4. So that has to be either a 5 or a 6. So there's only 2 ways out of 6, which is 1/3. This is funny. You can tell I wrote this in July of 2013. So probability of a day in July 2013 having been over 70 degrees. Oh, it was a beautiful summer. So we had 18 over 70-degree days that July, believe it or not. It was wonderful. Divided by 31, because there's 31 possible days, which was 0.58. You see what I mean? 18 out of 31. It doesn't make sense to me, but if I put it in decimal form, 58%. I can think about that and I can understand what that is. That's just the way our brains work. So those are basic probability. Not too bad yet, right? So what we have here, this is really interesting. So these are computer simulations, and we're tossing a balanced coin 100 times. So if I toss the coin the first time, of course, I get 1 out of 1. It's up here the first time I toss the coin. And then, of course, I toss the coin again a couple more times. And now 2% of them, or 20% of them, are heads. But as I toss the coin more and more times, my proportion of heads gets closer to what I expect it to be, which is about 0.5. And the same thing happened on the second simulation as well. This one kind of didn't dip down quite as far before it recovered, but it certainly can do that. And that's the interesting thing about randomness. You can have 5, 6, 10 heads in a row. People tend to, if you told a person to sit there and say heads or tails, they wouldn't do too many heads or tails in a row. That's how one way you can usually tell if something is truly random or if people just made something up to be random. Because true randomness will allow things that don't have a real high probability of happening does occur sometimes. So you're able to take a look at different number of tosses, and you can see that there's going to be stretches of all heads and all tails in those tosses. Okay, so let's talk about a few properties of probability. Okay, number one, this is a really, really important one. Probabilities must be between 0 and 1 inclusive, which means probabilities can be 0 and they can be 1. So what we're going to do is, oops, okay, that didn't work out like I wanted it to, did it? Oh, hang on. Change colors here. There we go. So they have to be between 0 and 1. So this means that if you get a probability that's negative, it's wrong. If you get a probability greater than 1, it's wrong. Okay, a little hint that you can do. So if you're figuring out a probability of something and you somehow get an answer that's either greater than 1 or negative, you know that answer cannot be right. Something is wrong. So it's something that you have to look at. One calculator note is your calculators will tend to put something into scientific notation as soon as it goes more than 3 decimal places below. So if you see something like 5.68732, it'll have a bunch of numbers here, 4, and then over here it'll go E negative 4. What that indicates is 5.6873214 times 10 to the negative 4, or we move this decimal place over 3 times, 1, 2, 3, 0, 0, 4 times, 4, 0, 5, 6, 8, 7, 3, 2, 1, 4. This is definitely a probability. If we just look at the beginning, we think, oh, the answer is 5.69 or something like that, and it's greater than 1. You would be very wrong because your calculator is automatically putting this into scientific notation already. So this is always something you want to look for. If you calculate a probability using your calculator and you get a number greater than 1, look for an E negative something over here. And that just means move this decimal place over to the left this many times. And that way you can get your actual answer, 0.00056871. You don't have to go that far. You could say 0.000569 would be perfectly fine. Okay, so having all that said, let's talk about what if the probability is 0. That means that the event cannot occur. Okay, this is impossible, an impossible event. Okay, think about you're rolling a die and getting a 7. That's not going to happen because there's no 7 on the die. If something must happen or always happens, its probability is 1. So if I'm rolling that die, what's the probability I get a number less than 7? Well, if it's a standard 6-sided die, the probability is going to be 1. Okay, so let's talk a little bit about sample space. Anytime you say space, people kind of go weird, but the sample space is just the collection of all the possible outcomes that you have. So a sample space for a die roll is either 1, 2, 3, 4, 5, or 6. Let's think about some other things. What's a sample space for a coin toss? It's going to be heads or tails, right? What's a sample space for 2 coin tosses? Well, that's either they're both heads. First one's heads, second one's tails. First one's tails, second one's heads. Or they're both tails. Okay, those are my ugly brackets. Okay. What about our marbles? Well, the sample space was blue, blue. We had 4 reds, or 5 reds. And we had 3 greens. There's my sample space for my marbles. So they don't have to be numbers. In this case, they are. They can be just heads or tails. They can be 2 tosses, so they can be 2 events coming together. Or they can simply be the marbles in the bag. So now we look at these events. So events are just basically something that happens. So what is the event of an odd die roll? These events, these are little subsets of your sample space. So the event of an odd die roll is either 1, 3, or 5. The event of rolling a 2 is just 2. In this case, the event of tossing a head is just H. In this case, the event that the first toss is heads, so the first toss is heads, is HH and HT. Here, the event that we obtain a blue marble is these 2 marbles. So there are 2 out of 10, just like we said the first time. Here, Venner rolled, there are 3 elements in here, 6 in here. So this probability is 3 out of 6. This probability, there's 1 out of 6, 1/6. This probability, 1 out of 2. This probability, again, 2 out of 4, or 1/2. The marbles, we just said. So we have, when we write down our sample space and we write down the set of that each event represents, then we can easily use our F over N definition of probability to find our answers. Okay, so once again, an event is one occurrence of the activity, of the probability being calculated. So if we're looking at the probability of dice, the event is one roll of the dice. A simple event is something that cannot be broken down into smaller components. Rolling 1 dice is a simple event. Okay. A compound event made up of several events. Rolling 2 dice. Okay. Throwing the rolling or flipping 2 coins rather. Something like that. Those things are compound events. Okay. Now, since we denote events, we usually denote these by capital letters, A, B, C, Sometimes I use a letter that makes sense in the context of the problem. And they're a subset of the sample space. So we have an event A, and we call its probability P of A. So this is P of A, or probability of A. Probability that event A occurs. And again, this is just written in symbols. Probability of A must be between 0 and 1, no matter what that event is. So if we think of an event B, the probability of rolling a 7 on one die, since it can't be a subset of the sample space, it's impossible. It's an empty set. Nothing is in it. So it becomes the impossible event, and the probability of B equals 0. And I wrote this wrong, so a typo here. If we think about event C, the probability of rolling a number less than 7, it's everything in the set. So if you think about C is 1, 2, 3, 4, 5, 6. And remember, our sample set is all 6, so it's 6 out of 6, or 1. Event B is an empty set, doesn't have anything in it, because the set has to be a subset of the sample space. And if it's not in there, you can't roll a 7, the probability is 0. So this is going to become very, very handy for you when you go to do your assignment. We're going to have some questions. So let's just look at a few. What is the probability of rolling a 3 on 2 dice? Well, each of these are my 36 simple events that can happen, because I can roll a 1 on the red die and a 2 on the black die, or I can roll a 2 on the red die and a 1 on the black die. So of all these simple events, there are 36 of them. So the probability of rolling a 3, I have 2 ways to do that, or 1 over 18. So that's one way I can look at it. Now, what if I say, what is the probability of rolling a 3 or 4? Well, there's my 3, and then I count my 4s also. So I have 1, 2, 3, 4, 5. 5 ways to roll a 3 or a 4. So that's 5 out of 36 ways. And so that's how we would go about doing that. So it's kind of fun. It's kind of just a game to play. It's going to be a couple of questions you guys are going to have on your next worksheet to do that. And remind me in class, I'll put this up on the blackboard, whiteboard. Okay, so here is a few things that we have when we're talking about probabilities. Just a few definitions. So this is A with a little c up top. There's a lot of ways to write this. You can write not A. Oops. So A complement can also be written as not A. It can be written as A with a little accent mark. It can be written as A with a line over it. Don't really like that, just because when we put a line over something, we're thinking of average. But these are all the way different books. Your book actually uses the word not A. I don't agree with that. My favorite is this one, which is why I'm using it, because it's you can almost say it, A complement. So it's A complement. It means all of the simple events in the sample set that are not an A. So if we looked at A is rolling a 2, then A complement is rolling anything except a 2. So the sample set, or excuse me, the event set would look like this. And then the next one we have is A union B. So these are all the simple events that are in A or B or both. In other words, it meets the criteria to be in either A or B. So let's keep A as rolling a 2. Let's make B is rolling an even number. So what events are in A or B or both? Well, 2 is in both of them, so that counts. 4, 6. I don't need to repeat 2 again. I only need to say it one time because I have it here and I have it here, but I don't want to repeat it in the union. So this is A union B. So looking at intersection, and sometimes people think of this as you take everything in A and you stick it into the cup, take everything in B and you stick it into the cup, and you don't repeat anything. So this union holds everything. So in intersection, we take everything in A and everything in B, and the only things that stick up here are the things that are in both. So if I look at A and B, what simple events are in both A and B? Well, A is just 2. And if B is 2, 4, 6, the only things they have in common are this 2. So A union B, again, is just going to be just the 2. So it meets the criteria for both of them. And that's the difference between these two guys. One way to remember union, this is a U. Intersection, this kind of looks like an N, sort of, not really. Okay, so here's some Venn diagrams for what I just said. So here's the not E. So if this is event E, then everything around it is the event not E. A intersection B, this is where they literally intersect. They're right here. And this is where we're going to find them. A union B, A or B, it's this whole thing and this whole thing. Now we have to be really careful. We don't want to count this twice. We'll get to that in a little bit. Okay. So the cards example. So let's talk about a deck of cards. We got a deck of 52 cards. Okay, we have ace through king. So we have 13 numbers, 4 suits. So let's talk about event A. Event A is the probability of rolling the king of diamonds. What is the probability of A? Well, we have how many favorable events? There's one. There's only one king of diamonds in the entire deck of cards. And the entire deck is 52. Okay, we can do that. Event B, any of these 9s, 4 9s. So it's just the probability of rolling a 9. So we have how many 9s in the deck? 4 out of 52, or 1 out of 13. Now we want the probability of rolling any, or not rolling, choosing any heart from a deck of cards randomly. Well, there's 13 hearts out of 52 cards, 1/4. This is black cards. I just couldn't get them all on here. So the probability of D rolling any black card, well, there's 4 suits, 2 are red, 2 are black. So we know that we have 26 black cards out of 52 cards, which is 1/2. So let's think about these 4 events and let's see what we can do with them. So let's take a look at them. Here's the Venn diagram. So here's my sample space. So up here, I have the king of diamonds. Over here, I have my nines. So let's see. This right here is my 9 of hearts. Here is going to be my 9 of clubs and my 9 of spades. Here is going to be my 9 of diamonds. Those are all kind of in different places. This is the other spades and clubs. This is the other hearts. And out here is my other diamonds. So now we can really see what's going on. And this covers event C. So we have this deck of cards. All of the hearts are in here. The 9 of hearts, as you can see, is in both B and C. So let's talk about some probabilities. Let's take a look at what if I want the probability of B intersection C. So that's these two. Well, how many cards do B and C have in common? Just one. So that's going to be 1 out of 52. But now let's look B union C. Let's think about that one. Now I want all of this, and I want all of this. So think about it. There's 12 cards in here. There's 1 here, because this makes 13. This whole thing is 13, 14, 15, 16. So I have 16 out of 52, or let's divide that by 4. What did I count? Oh. No, I counted 13, 14, 15, 16. Yeah, I did fine. So divide that by 4. 4 out of 13. So now there's 4/13. A card being either a heart or a 9. And notice I didn't count this guy twice. I did 12, 13, 14, 15, 16. I counted my favorable outcomes out of the total number of possible outcomes. So let's try that again. What if I wanted the probability of B intersection C, or D rather? Well, if you look at this, how many does it have in common? 2 cards. 2 out of 52, 1 out of 26. But if I wanted the probability of B union D, well, how many cards? All the other clubs and spades are in here. Or I can also think of this whole thing right here as 26, 27, 28. So that's 28 out of 52. Or divide by 4, 7/13. So one more thing I want to look at. What is the probability of A intersection B, let's say? Look at A and look at B. Do they ever intersect? No. So the probability of A intersection B is 0. It can't happen at the same time. I can't have gotten the king of diamonds and a 9 at the same time. Therefore, if I want to look at A union B, that means I either get the king of diamonds or I get a 9. That's 1, 2, 3, 4, 5. I don't have to worry about double counting anything. I can just count the number of outcomes in each one and be done with it. So 5 out of 20, 5 out of 52. What if I wanted to look at what is the probability of C complement? So the probability I'm not C. That's the probability it's not a heart. So well, there's 13 hearts. So the rest of them is 39 out of 52, which is, divide those by 13, 3 out of 4. So that one's pretty easy to do. Okay, so let's talk about the maternity stay example. Now, what's nice about this particular problem is each one of these, none of these overlap. All of these probabilities are part of a whole. So if I were to make, say, a diagram for it, basically, I would have something like this. So this is 1, 2s, 3s, 4s, 5s. And that's what that's going to look like, because this one only happened 0.188, this one happens 0.252, this one happened 0.441, this one happened 0.15, and this one only happens 0.039. So if I want the probability of A, that a woman stayed in the hospital exactly 3 days after she had her baby, then I can get the probability directly from this list. It's 0.441, 56 over 127. If I want the probability she stayed less than 5 days, well, look how I did that. I said, well, that's 1 minus the probability that she stayed 5 days, which was 1 minus 0.039, which is 0.961. Now, at most 2 days. So what does at most mean? 2 or less. Well, no easy way to do that. I can just take these probabilities and add them up. This one, because they don't overlap. So there's 15 women in here. There's 32 women in here. So I'm just going to add these two together. So I can think of this as 47 out of 127. Or I can simply add them from here. It doesn't make any difference. And it's 0.37. At least 3 days. So that's 3 or more. 3 or more. So that's these three. So I can add them up from this point and divide them by 127. So I can go, okay, that's 75, that's 80 out of 127. Or I could add them up at the probability level, because all of these are just simply divided by 127, 0.63. So, fairly simple when there's nothing that overlaps and you don't have to worry about double counting. Not doubling, double counting. Because nothing overlaps. So this brings me to this new definition, mutually exclusive. So 2 or more events are mutually exclusive events if no 2 of them have outcomes in common. So looking back here at the maternity example, if the patient stayed 1 day, they didn't stay 2 days. If they stayed 2 days, they didn't stay 1 or 3. So this was simply how many days did they stay in the hospital after they had their baby. So these were all of these simple events were mutually exclusive. So the probability that they stayed 1 day union 2 days was mutually exclusive. And we can just add their probabilities. So, I should say or. 1 day or 2 days. These were all mutually exclusive. So every single one of these was mutually exclusive. That's not to say that these events are mutually exclusive, because some of these did overlap, but the simple events, these 1, 2, 3, 4, 5, or 6, those were mutually exclusive. Now consider events C and D from the previous example. So if we looked at the card example, remember C was hearts, D was spades and clubs, those two are also mutually exclusive. And so was A and any other event. And you'll notice that when you look at something that's mutually exclusive, the probability that they have an intersection is 0, because there's nothing that can be both a heart and a spade or club at the same time. So we also have A and B. That was 0. The probability that the patient stayed 1 day and 2 days, 0. You couldn't stay both 1 and 2 days at the same time. You either stayed 1 day or you stayed 2 days, or more than that. So that's how we can look at things that are mutually exclusive. So let's take a look at what that looks like on a Venn diagram. So in a Venn diagram, of course, we don't overlap. We have no intersection. And here, these two things are not mutually exclusive. There's an intersection here. So we have an intersection. So these are mutually exclusive. This one is not mutually exclusive. So let's look at 3. Here we have 3 events that are all mutually exclusive, like the maternity stay example. Here we have 3 events that are not mutually exclusive, like the cards, B, C, and D. We had something similar to that. Maybe we didn't, not quite. We didn't have any B or C weren't together. And then these are both not mutually exclusive, because even if you have 3 events and 2 events are not mutually exclusive, then we say that A, B, and C are not mutually exclusive. So in the card example, A, B, C, and D are not mutually exclusive, even though we have A and B are, A and C are, A and D, and C and D are all mutually exclusive. But the 4 events are not mutually exclusive because some of them overlap. B and C overlaps, B and D overlaps. Okay. This one we will start on next time. Just kidding, I'm going to do this last example. We're going to do this actually in class, maybe not this time, but maybe next time. So we will actually do this with our class, but this is another class that I had previously. And in that class, I had 23 right-handed females, 12 right-handed males. Oops. Sorry, hit the button at the top. 12 right-handed males for a total of 35 right-handed people. I had 2 left-handed females, 3 left-handed males for a total of 5 people, left-handed. And so that made 40 people in the class, 15 male and 25 female. So the first thing I would like you guys to do is, can you tell me what is the probability that a person selected at random is female? We take the number of favorable outcomes, 25, out of the total number of people in the class, 40. And let's divide those by 5. We get 5/8. So 5/8 of that class. So what is the probability the person is left-handed? So I had 5 left-handed people in my class out of 40. So this is 1 out of 8. So now let's consider the probability of A intersection B. So they have to be a person who is female, and they have to be a person who is left-handed. How many of those people do I have? Yes, 2. So I have 2 of those people. That's this. Out of the 40, which was 1 out of 20. So looking at this one, probability of A union B. So this is people that are female and people that are left-handed. So I have 25 females, right? And then I have an additional 3 people who are left-handed males. So what if I just add these 2 people up? 25, 26, 27, 28. So that's 28 out of 40, which is 7 out of 10.7, if you will. So that is it for this one, and we're going to start rules of probability next time. Actually, we're going to do rules of probability for this one. I'm sorry. So let's talk about what we just looked at. So we've kind of already discussed this, but when we do unions, we want to take all the probability of all the events in A and the probability of all the events in B. However, what happens is when you have events that are in both of these, they end up getting counted twice because this intersection is a subset of A and it's a subset of B. So when you add these up, you end up double counting the intersection. So subtract 1 off. So looking up here, back to this example, look at this union. If I have 25 over 40 plus, so this is my females, my left-handed people, I need to subtract off my 2 left-handed females because I double counted them. They're in here because they got counted this way and they get counted this way. So I end up with 28 over 40, just like I did before. And I could have also done it from this way too. I could have said, well, I have 5/8 plus 1/8 minus 1 over 20. So that's 6/8 minus 1 over 20. So let's make this 40. So let's see, that's 5, that's 30 out of 40 minus 2 out of 40 is 28 out of 40, and I get the exact same answer. So I can do this from the probability level if I don't have the actual numbers. So let's look at these. Here's the card example. So remember, probability of B was 1/13. That was getting the 9. Probability of C getting a heart was 1/4. But remember, if I simply add the probabilities, I get 17 out of 52. We know that was wrong because we ended up counting the 9 of hearts twice. So in order to find that probability, we've got to do it this way. We've got to do 1/13 plus 1/4 minus 1/52, and we end up with 16 52nds instead of 17. So what happens when the events are mutually exclusive? Well, when the events are mutually exclusive, remember their intersection is 0. They don't have any events in common. So are you double counting anything? Well, no. So in the maternity example, notice we were just adding the probabilities because we could. And that's what's nice about that. I don't have to worry about subtracting anything because I'd be just subtracting 0 anyway. So if I had the probability of drawing the king of diamonds or a 9, so that would be the probability of A union B, the king of diamonds, which was 1/52, a 9, which was 4/52, then the probability was 5/52. And that's what we did before. We simply just counted them up because we didn't have to worry about counting anything twice. and then finding the probability that something does not happen. So this kind of makes sense, because if I want to find the probability of A complement, that's just 1 minus the probability of A. So if I want to find the probability that we did not get a heart, then that's the probability, I believe that was C complement. That was just 1 minus the probability of C. So remember, this was 1 minus, this was just 1/4. And remember, that was just 3/4. And you can also do this backwards. Probability of A is 1 minus the probability of A complement. It's very, very simple. So I love the complementation rule. This makes your life so much easier. It helped us a lot. If you look back at the maternity example, I go back to that real quick. Right here, I wanted to show you this part B that we did. Part B was, what is the probability they stayed less than 5 days? So we used complementation rule. What was 1 minus the probability? Well, that they stayed 5 days, because 5 was the highest number on here. So it has to be 1 minus this number, and we didn't have to add these 4 up. You could have definitely added them up, and you should get the same answer or very close. Sometimes there's round off error. But we used complementation rule already. So nothing's really new in section 4.3 that we haven't already done. And now I can call myself done for today.